I woke up this morning tremendously ill, so I apologize if I sound like I've been kind of punched in the head or something. It's not me, it's just the lurg. So, HelloStavanger, do you have to open every talk with that? I hope you've had an excellent conference so far, and so thank you for being here. So, my name's David, and I've arguably made my career from fixing kind of broken and damaged systems. And more importantly, taking systems and turning them into sometimes good, and with kind of the right tailwind and the right people and the right phase of the moon, like kind of occasionally systems that pay the bills, right? The ones that you all grow to hate, that eventually live, that everyone complains about in 30 years' time. Kind of legendary systems. And this talk is about that process and about how the weight of the systems, something that's often really hard to comprehend, has this lasting effect on the kinds of software that we design and how it interacts with both the people and the communities that maintain them. So over the last couple of years, I've been talking about something called intentionality in software design, which is about how only systems implemented with kind of this extreme care really have any shot of becoming great systems. Systems implemented with like the slavish obsession of artists doing their most essential work. And this is something of a companion piece to that concept of intentionality, where I zoom up and out and think about broad-scale system design. So if you've heard anything about me in the past, don't be surprised if there's some shared themes between those talks. And I forgot my little clicky pen. Clicky pen. It's great. Okay, so let's start with something you can all probably understand. So who in here can show me how long a 30-centimeter ruler is? Kind of that big, right? We kind of got it. Yeah, so hands up if you can visualize in your mind's eye a kilometer. Yeah, kilometer? Some people, anyone, hands up, anyone can think? Do you have like a kilometer in your head? Okay, cool. So I have a really specific story. So for me, a kilometer, well, the house that my mother lives on is at the end of a road with a weak bridge on one end. And at the other end of the road, there's a sign that says, weak bridge in a quarter of a mile. So I kind of know that a kilometer is kind of up and down that road a couple of times, rounded a little bit. And it's ridiculous, but I think it's really illustrative of the way that humans relate to scale. Like we try and internalize examples to keep us grounded. Okay, next question. How big's a megabyte? About that big, right? Floppy disk. So to me, and I think this probably ages me really precisely, a megabyte is like 128 kilobytes per second MP3 file that I stole off the internet, probably from Napster. Right? That's what a megabyte is. It's a minute of music. Well, 960 kilobytes, and we'll save the 40. Okay, how about a gigabyte? Yeah, a little bit less than an hour of an MP4 movie at 720p. Probably from the Pirate Bay. So I'm getting a little bit less accurate as I go, and I think we can conceptualize via analogy that digital storage sizes across mediums, just due to this kind of lifetime of being exposed to all these different things. But there are kind of two problems with this when you start to relate it to software. And it's kind of the reason this meme exists, right? That you don't really know what a billion is. Or this one. And, you know, we've seen a lot of different versions recently of why billionaires are probably bad, right? Lots of lived examples in the world today. And also this meme about how your understanding of scale changes as the numbers get big and it becomes increasingly impossible to comprehend. Now, I can tell you right now that while I can tell you how to visualize a megabyte or keep it in your head, or a gigabyte, maybe even a terabyte, I have absolutely no frame of reference for what like a petabyte is. Is that a data center? I don't know. Like, no idea. And the next problem is somehow even more complicated when we start thinking about size of things. And that's the size of your software in terms of the amount of complexity that it can contain and all of the capabilities that it expresses is really not directly related at all to the number of bytes that it occupies on your disk. This is like, you know, complexity explicitly is not the same as raw size, and we've had these bad measurements time and time again of people who try to measure kind of the qualitative nature of software in lines of code and other really terrible metrics, right? So all of those things are no more than a rough indicator of scale, but what they don't do is they don't capture complexity or accurately describe the challenges of working inside of a code base. And so complexity obviously is a measure of how hard it is for your brain to compute or internalize a system. It's the stuff that you keep up here, not how much code there is to read. Though again, a measure can help to be a leading indicator towards helping you understand which things are hard and which things are easy. Now, this really difficult mix of size and complexity and scale wreaks absolute havoc on the way we design our systems, because getting it wrong leaves you carrying this kind of burden of complexity that will often outmatch your organization, and it will leave your software to kind of atrophy and stillness. The same problem affects a lot of different aspects in software, actually, from understanding complexity to design to estimation. They're all fundamentally related to the human brain's lack of being able to comprehend scale and how it represents complex things. So, a couple of years ago, I wrote this talk called Intentional Code, and in it, I used this one phrase to describe complexity, and that was that the complexity of your software should be, at most, as complicated and ideally less than the problem space that it inhabits. Right? Because if you're building something that's more complicated than the problem domain, you actually made the situation worse by adding software, not better. And I said that to capture this idea that if you're building complicated answers to simple problems, you're likely backing your implementations into a corner. And the more I've thought about this idea over the last couple of years, I've reached this kind of complementary idea about what gives your software this feeling of being too big or too much or the wrong size. And that it's that you actually respond to the surface area of the systems, not actually the depth or the lines of code. It's the observable set of things that you can see when you're doing maintenance that you have that guttural response to. And I personally just think that's what affects people. The total sum of the interfaces we're exposed to, the number of moving parts, and the sum of the data structures in the software. Not, crucially, the depth of complexity contained inside the abstractions. Controlling that surface area, your software design and your subsystems and your modules, is important for any system that survives. Now, this is exactly the reason that you think code that accesses the file system is simple. Right? It's just files and directories. And when you look at, say, a trashy enterprise application with thousands of boilerplate lines of code, you think that is complicated because it looks big and sprawling. Despite the fact that actually when you think about a file system API, it contains like a vast complexity of spinning disks and SSDs and native APIs and operating system compatibility. But what it really does is it describes that problem space in a really neat way where you can keep it in your head. So it's the surface area that counts. And I think the real epiphany for me when I stepped back from software implementation into thinking about this in terms of broad-scale system design was I saw the exact same pattern repeating at larger scales. So architecture tries to solve this, right? It tries to solve the surface area problem by containing complexity in various ways. But is software architecture in its current form actually a really good answer to this? Now, one of the reasonable answers to that question is, to the question, what is architecture, is that it's the big decisions that you make when you're building systems, or the decisions that are difficult to unmake once they've been made. And I could talk for an hour about the different descriptions of what architecture really means, but I kind of, for brevity, I just stick to the definition of large-scale system design. Now, architecture is really explicitly concerned with trying to contain complexity and direct the design of your system. So by definition, it's kind of a significant part of the job to attempt to contain or control or provide a good answer for complexity that comes with really growing a system to scale. That's really the challenge. Now, the path to containing complexity leads to some really weird places, and it can be especially damaging to the architecture of our systems in the ways that we often build them today when you try and contain things. Now, the system that I'm currently building in my day job was kind of forged in the shadow of 1,000 failed attempts to understand and contain complexity, and really a failed attempt to work out what the right size for the solution was. Now, the original system design was, I like to think of it, it was born at the height of the misunderstanding microservices boom, where everyone thought that every microservice meant one function and basically shot themselves in both feet with the two biggest fuck guns they could find. So everything is a microservice. Everything must be a serverless function. Everything should use Cosmos DB for storage. These were like diktats at the start of building this system. And so many other kind of vast, grand proclamations of all X's are Y. Everything of this must be that. And it's taken the teams that I work with kind of half a decade to start unpicking and course-correcting some of the pain that these really blunt design instruments cause on the system. So uniformity in design is probably the original sin of software architecture, right? Thinking that everything has to be this one thing. Just absolutely terrible fucking decision. Because in trying to make everything uniform to contend with perceived complexity, the real outcome is systems that just don't fit their context. And that leads to brittleness and eventual failure and stagnation. So designing your systems around technology choices rather than outcomes is just like this perennially bad idea, right? We know this. And this is the pain that I feel every single day. And the problems I've encountered trying to kind of consolidate this fundamental technical misunderstanding of scale reminds me of another really famously shared system design. Anyone seen this before? Right, this thing. So I'm reminded of this. This was published by the challenger bank Monzo maybe 5 or 6 years ago, maybe even 7 years now. So at the time that it was published, which was again at the height of the microservices boom when everyone was doing the microservice transition, Monzo talked about having 1,500 microservices. And things that they publish today put the number closer to 2,800. And I can kind of see a little bit of like the gasps in the audience of like, oh God, that seems like a terrible idea. Kind of. I'm hesitant to criticize somebody else's system, right? Because I'm not responsible for it. And everything exists in a context. But I'd feel deeply uncomfortable about any system that contains this amount of resting connectivity complexity. Like the number of possibly failing moving parts in that is scary to me by default. I feel like this diagram that Monzo published received a lot of criticism from the community for 2 reasons, though. Firstly, if you don't live inside of this system and you have no context, it's really difficult to imagine what that design could exhibit that would kind of match people's mental model of what a bank does. Like, what are the 2,800 things a bank does? It's just not what people have in their head. And this isn't specific to Monzo, right? Everybody's business looks much simpler from the outside. And I have extreme sympathy, especially in banking. It's really, really actually very complicated. But people's mental model of the space is much simpler based on the surface area of it that they observe. And secondly, I think there was some valid criticism directed at it because it was maybe appearing to celebrate this degree of distributed complexity. And when in reality, I think actually what they were saying is, look at how we survive this complexity. Look at what we do as a technique to get us through this design. Not, hey, everybody, we've got 2,800 services. Why don't you all go and cut your systems up into 2,800 moving parts? So I think people maybe misread the reason that they were publishing this piece. Unfortunately, in the technology world, so many people are full of systems envy, where they frequently kind of copy other people's homework and get bad outcomes because they think they're going to be the next whatever this other company does. So the picture that I'm trying to paint here, though, is that right-sizing a system is really difficult, and that the traditional technology-oriented view of trying to solve it seems to only lead us to complicated distributed failures. Now, it feels to me like this lack of comprehension of size is the root cause underneath the truism of Conway's law, that teams design systems that their organizational culture matches and the relationships inside of them. Right? This happens by default. Like, lots of people think Conway's law won't happen to them, but like it really does. It's a truism. So you either have to consciously produce a design that doesn't reflect your organizational topology, or you are doomed to accidentally model it. Right? It just happens. And I think you have to be really mindful about the way organizations can change when you're designing your systems, to ask yourself the question, what does our operating model look like in the future, in order to not feel the pain of this? So I've got this sense in recent years that the technology industry has gone through the growing pains of large-scale design. And as more and more people have had to engage in growing internet-scale systems, that many mistakes, including the ones that I've ended up trying to resolve myself, have been side effects of the difficulty in understanding this scale. Combining this with the literal application of, this is kind of awkward, really simple soundbite advice from people standing on stages at conferences, very awkward. Mixing those two things together, and this like oversimplification of design problems has got much more significant as a problem, because we've also lived this transformation in the same era as cloud computing has reached the mainstream. So it's been possible for the past 15 years to solve all these problems by just pouring more compute onto the problem, just put more stuff in, and having this really maximalist approach to software. And this is really unfortunate to get our heads around, right? That something that has generally been helpful, the commoditization of cloud infrastructure, has been equally harmful by effectively removing design constraints from all of our systems. Now you can just pay more money and do more. But you no longer have to find like a constrained solution, because more is more, perfectly capable of just being more. And this leaves us with this complicated design quandary. If the traditional tools of architecture, trying to contain the world, seem to fail us and lead us to like this explosion of complexity, how can we chart the course of large systems without making the same mistakes? So this line of thinking really took me on this journey of having to reconsider what the role of design and architecture is in the current software climate. Now, I always remember this really rough quote from an interview with Harrison Ford, actually, about the process of filming Star Wars. It wouldn't be a tech conference without some weird sci-fi thing, right? So George Lucas made a beloved franchise. He had points to make in his stories, but he was a notoriously shitty scriptwriter, like famously shitty scriptwriter. And it's claimed that much of the success of the original Star Wars trilogy was actually down to the editing of his then wife, Marcia Lucas, who was a famous Hollywood script doctor. An influence that was lost after their divorce in roughly like 1990, which might explain a few things about some other films that subsequently came out. So anyway, as he tells it, Harrison Ford was struggling with a series of like takes on one of the Star Wars films, and he got into this argument with George Lucas because the dialogue was so bad, and he basically like yelled at him, "George, you can write this shit, but you can't say it," right? And I've always been amused by this quote and the dynamic that it implies, because I think it's similar to the difficulties that architecture as a profession has in the changing face of technology, where more and more implementers have more things to say about the design of systems because they live them. Where increasingly complicated systems have been designed as boxes and lines by generations of like TOGAF-styled software architects that just never naturally meet implementation. Like they just don't look the same when you get there. You know, the architect used to be like a film director, whereas actually I've always thought that to be a really successful designer of software, what you really have to do is appreciate both the micro and the macro design. Like if you don't have an implicit understanding of those two different ends of the scale, you're going to either build a software design that doesn't fit or an implementation that can't grow, right? So someone that designs software needs to be more like an executive producer than a dictatorial director. And it seems to me now that anyone that looks at the design of large-scale systems from only one of those perspectives is doomed to build something that fails. So it kind of made me reflect that thinking of architecture as a distinct discipline from code is always a mistake, precisely because they're codependent things. So we're in a tough spot. Systems are bigger and more complicated than ever, and the constraints that previously used to keep them contained are loosened by cloud computing. And traditional architecture, through the lens of organizations and practices like TOGAF, kind of buried itself in so much bureaucracy that it's too far away from the work to be useful. But these systems and these problems aren't just going to go away, so what do we do? I want to talk about some of the tools that I try and use in my day-to-day job to try and kind of bring some sense of calm back to the chaos of over-design and over-distributed brittle systems. So firstly, everybody has to do design. And you'll notice I don't use the word architecture here because I think if you talk about it in terms of design, it's much more honest. Rejecting traditional big upfront lines and boxes design processes doesn't mean that you should stop doing design. To me, it actually means the opposite, that you should be doing much more design. Your system has a design, much like Conway's Law. A design will emerge if you don't think about it, and then you'll be stuck with an accidental design. There's no such thing as no design. One of the most important changes to me in my day-to-day working pattern was to try and invert the power dynamic between the people that were holding architecture or design jobs and turn them into people that helped people get to good designs rather than provide people with designs to implement, right? So they had to become people that helped navigation. I think this is vital in any organization because it helps scale out the ability to design solutions whilst putting people who hopefully speak the language of design right there with the people doing the implementation. Because the real challenge to make design a normal thing to do again involves establishing a culture where doing design is a very, very normal thing and not time-consuming, and by establishing a context and a language around it so people know how to communicate. And the context is probably the easy bit. It's your business, it's your volume, it's your scale. I've seen a lot of businesses really harm themselves by spending huge amounts of money designing systems for businesses that they're not actually in. Overextending themselves and saddling themselves with kind of business and technical debt, operating complicated things because they were dreaming of a future, not the place they were actually in today. The best system designs are literally the ones that match the problems you have today. And the second best system designs are the ones that match the problems you're about to have. I once shut down a project that had been in development for 2 years. Well, I shut down a hosting infrastructure because they built 3 entire Kubernetes clusters to run a single website. They were giving Google £45,000 a month for 10 developers to build basically a single page app, right? Because they knew they were going to be massive. So every design is temporal, right? It fits in a place of time, and you should expect it to change. A design that doesn't change probably wasn't a perfect design, and people have fallen into this trap so many times of thinking because they didn't change the thing that it was right. It's more likely that a design that doesn't change is a design that's actually constrained you without you realizing. So I try and establish ground rules and make sure people engaging in designs, whoever they are, know who and what you're designing for. Write it down, like yell it out loud, have design goals explicitly. Out of curiosity, does anyone have design goals for their software that they could just reel off? Interesting. That's not a criticism. So, in my day job, I have this single phrase that I use to drive out the design of our system. We build a credit card platform, don't worry about it, not interesting. But it's just a single sentence that I use when I need to tap the sign, which is we're building a credit card system for 10 years in the future when credit cards don't exist. And every incidental design goal that we make has to lead us back to that one statement. And if you asked anyone in my organization, about 400, 450 people, they would probably be able to recite that phrase by heart because I say it enough to keep everyone focused on it. It's like a simple statement of intent that captures the essence of everything we're trying to do. And you have to work out what your version of that is if you want to build something that truly succeeds in its goals. Now, the next most important thing to do once you've established the context that your system exists inside of is to express the set of common trade-offs that you're most comfortable with. Now, that's all software design decisions really are, right? They're the set of trade-offs where one side mostly satisfies the thing over the other side for the majority of problems. Now, every design decision is a trade-off between something and you have to give your teams a uniform language to describe them so that they don't find themselves making seemingly arbitrary decisions and accidental design. Now, this isn't new thinking. So ATAM, a method for architectural evolution. This was developed in the year 2000 at Carnegie Mellon University. And while it was presented as like a boring old architecture discipline, at its core, it was just a process about thinking in terms of trade-offs. Now, I'm not here to sell you a process, but I find it quite ironic that even when the desire is the same as ever, the problem with things that launch as methodologies is ain't no one going to read that shit. Like, no one's going to read it. So here are some examples of the design trade-offs that I make. We can start with some obvious things. Consistency versus latency. Cost versus performance. Availability versus cost, very relevant this week. Basically, everything versus cost is your first core trade-off. But there are lots of more subtle design decisions that you make sometimes subconsciously as well. Fidelity versus speed. Interactivity versus automatability. Stability versus feature richness. It might seem weird to evoke the Agile Manifesto, but one of the things that the Agile Manifesto did really well was articulate everything as being a set of trade-offs. We prefer things in column A over things in column B in all cases. The format works, so I would recommend you articulate your trade-offs for your system and use them to tap the sign. Now, because it's impossible to know exactly which trade-offs your teams are going to be making as they design some software or system, I like to articulate characteristics that the eventual design will exhibit that I prefer. So, for example, let's say you're designing a system that deals with vulnerable customers. And you design that your system should always optimize for customer safety. That's a characteristic of a system. And that no feature should ever cause harm or duress to your customers. Now, articulating that as a characteristic helps guide the design decisions that you bake into your system design, while being general enough that it's not prescriptive and it doesn't constrain your teams. So, if I was faced with, for example, two designs for a feature, where if an error occurred with one, a customer would be maybe forced through some support process, or maybe they were charged twice and we had to do a refund, or another option where a failure would cost the company a bit of money or take some manual effort to rectify. If that top-level characteristic was true, that we didn't believe in causing harm, you would always choose the second option, always. And because you've done that, taking this approach helps people both articulate why they're making the trade-offs they're making in their designs, but it also keeps you focused on the real outcomes of your work. Like, what does this look like if we get it right? So it's funny, but I think I learnt this from a silly pirate video game. So I spent about 3 years playing an online game called Sea of Thieves. It's made by Rare, the people that made GoldenEye on the N64 and Donkey Kong and Banjo-Kazooie and all sorts of stuff. Sea of Thieves is like a multiplayer sandbox-ish game, and while I was watching some of their behind-the-scenes developer diaries during lockdown, I thought the way they articulated the things that they put in the game as tools, not rules, was a very, very nice, pithy statement to capture this intent. So as part of establishing your shared language of trade-offs, it's useful to have some archetypical designs for all the boring things you do all the time. So it's a thought I've been coming back to more and more as the system that I look after sprawls out in front of me, that localized design will often be novel because the system is of such a size that cohesive design basically becomes impossible. You can't look at everything, it can't be coherent. But what we can do is we can give people touch points, a few patterns and a few tools to communicate with other teams living in the same software ecosystem. So the more that you equip people with tools, be they patterns and practices for implementation or protocols for communication or even processes between people, you enable novel design in the corners of the system. You basically permit them. You say, we know that other things might look weird, but that's okay because the edges are all expected. And I think that allows innovation to flourish in large distributed systems and in larger organizations as they grow. Like, it's kind of okay. And what I've tended to observe is as these novel pockets of design spin on their own, the broad implementation of the system tends to coalesce together. So rules introduce constraints to a design, and there is some utility to that. You don't want to invent logging 60 times if you have 60 teams, right? It's stupid. But actually, those constraints provide freedom because they let people spend their time thinking about the interesting problems in the different pockets of the system. Now, is there a single good design process? Everyone gets so focused on process, especially in business, right? Everyone loves a process. It's my belief that your design process should be as cheap as possible. Whatever it is, just make it cheap. That means that you should use methods that are most appropriate at expressing the designs you're trying to articulate. So sometimes that means drawing boxes and lines. Maybe that's the cheapest way to articulate your design. But other times you want to choose something closer to the implementation to feel the ergonomics of a design out. I always think that HTTP API design is one of those facets of design that most illustrates this concept. It's really, really easy to get a piece of paper and draw a box that says API, database. But the number of APIs that I've sat with where at the low-level implementation of the contracts are just like, who did this? Like, did anyone imagine what it was like to use it? It's a visceral reaction. And actually, I find that when people are doing design of those kinds of systems, just go straight to the code. Go straight to the metal. Like, you don't need to sit and write documents or write specs. Feel it out, and then lock your design in. Don't fear doing spikes and implementation before a design is final. This idea of a final design, of course, doesn't exist. So one of the failings of traditional software architecture is, in my opinion, it became so focused on process and too rigid, and it almost kind of disposed of the one great thing that we have in software uniformly. It's really cheap and easy to change software. We have source control. Like, you fuck it up, you roll it back. Don't worry about it. Like, you can experiment. And I think this is all because no design meets implementation unharmed. Never. I have never seen it in 32 years of programming. I've never seen a design start off on a piece of paper that was then implemented and was good. I've seen a couple that were bad. This is also why it's not advisable to try and center yourself or a single team in the middle of a design process. You can do it, but you're making this really distinct trade-off that speed and bottlenecks are acceptable with the reward being uniformity. And that's okay if you value uniformity. You can make that trade-off. It might seem like a good design decision, but it works to a point, and eventually you get your system to a place where it outgrows you. Right? And then you won't be the best person to make decisions. And if you've centered yourself or a team in the middle of the whole thing, what you actually did is you taught a bunch of learned helplessness into all the teams that should have been doing design the entire time because they didn't get to practice doing incidental design when the stakes were low. So you get all the way to the place where you've got a big complicated system, and then you say, hey, everybody, time to do some design, and they panic because they never practiced. I think this is the trade-off that traditional ivory tower architecture makes, and that's why it failed, in my personal opinion. And I would caution against doing it ever. Okay, so where does it all go wrong? So back at the start of this talk, I was thinking about how so many systems seem to kind of swing and miss at this. They all fall into the foibles of dictatorial uniform design and rigidity and this myth of prediction. They form systems that they think can accurately predict the future state of the world. If I could do that, I would buy lottery tickets every week. And it begins to weigh everything down. So first, let's talk about the core crime of boxes and lines design. Boxes and lines often get literally interpreted and subsequently lead to systems that are over-decomposed and really, really codependent. And this is probably the central crime of what went wrong with microservices, is people drew a lot of boxes and lines. Now, diagramming is really powerful, where entire subsystems and dependencies and deployable units of code can trivially be placed on this big dungeon map of a system without the real-world consideration of what the extreme cost of components really is. Like, I regularly stop people in my day job from subdividing the system into smaller components. often the motivation is because a boxes and line diagram contained a mixture of what looks like systems and also logical steps. So people are trying to model a process, yet they then interpret the process as moving parts. And the truth is this: additional components in a system never come for free, ever, even if the cost of infrastructure is kind of marginal. Right? So you add something to my system, cool. Repository management, documentation, build pipelines, security scanning, patching and freshness concerns in container images, testing and verification, runtime latency. That's all the stuff I just got for free for you adding a system or a service or a function. Taking a step in a logical application and just extracting it out through either some kind of slavish obsession to single responsibility principle or to match some big dungeon map diagram often has all of these second-order effects that basically far outweigh the benefit you get of just separating something out so it can run on its own. Now, one of the things I try help teams I work with understand is when it's really the right time to do that, though. If we're going to pay all that cost, what do we get? In my view, unless two parts of a design have either an order of magnitude difference in usage scale, different deployment characteristics, different traffic profiles, or different failure and recovery semantics, you basically get to pay all that cost of decomposition without a single solitary benefit. You would be better with one monolithic application. In fact, I tend to find that most attempts to split up a system are really secretly attempts to hide, or at least move out of sight and out of mind, some technical debt that's accrued in an existing system component, without really thinking about solving it. So the urge to just make a nice new thing is really strong in programmers. We all like looking at nice new things that we understand. But normally that comes from not understanding the living system that they're operating inside of for individuals. And it's almost always the wrong reason to make a decision to split something up. Like, complexity in any existing system should be faced and not avoided. It's a conflict avoidance technique. And a friend of mine always says that conflict avoided is conflict multiplied. And I find in distributed systems, if you subdivide a component so you don't have to look at that shitty piece of code, you just bought 10 problems rather than solved one. So I like to think of all this stuff in terms of what I call fault boundaries, which I suppose is really my own reinterpretation of DDD-style microservices. I use the term fault boundaries to escape the trap of over-relying on the word service, which often implies things about deployable units of code or logical processes. Now, to me, inside a fault boundary, things always fail together. So increasing any resilience inside of a fault boundary has no effect at all on the availability of your system, and often, in fact, splitting things inside of that fault boundary into more finely grained services is literally just a poor design trade-off, because you're paying all that cost of complexity without the benefit. So you can really identify the fault boundaries in your own system by asking one simple question, which is, what else doesn't work if this fails? If you see a lot of moving parts that all fail together, they're probably best served as one logical deployable unit without any of the buffers or inter-process hops or kind of any other SOA frippery. So consolidation is a tool that you have to put sanity back into these overly distributed systems. Now, when I talk to my teams about this, people often just say, oh, but what about scale? And I always think that people use this idea of scale as the reason that they might want to decompose a system, but without actually having a definition of what scale really means either. Now, for me, there's only really 3 kinds of scale: fitting more users around a system, fitting more programmers around a system, which is actually the most common cause of scale, and fitting more features into a system. I find it useful when people say, oh, we need to do this because of scale, to say, and which kind of scale do you really mean? Because often, again, systems get forced into premature decomposition by trying to meet a scalability goal that actually isn't a requirement, not an expectation of the system, but they think that everything has to scale. Okay. So if understanding scale and fault boundaries are good reasons to decompose software, yet people often reach for decomposition as a reaction to existing technical debt and accidentally increase the complexity of a design, we're forced to answer one question, which is, where is the right place to put complexity then? Like, we've still got logic. I have two answers to that question that have always served me really well. The first is very traditional. Modularization and abstraction inside of an application is the design tool we have to contain complexity. When you're tempted to decompose and divide a system into components, first ask yourself, can I meet the same goals I'm attempting to reach by simply designing a better abstraction or module boundary? Because if I can do that, that is cheap and easy, and I should do that first. My second answer is a bit more facetious, I suppose. Never, ever, 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 ever put the complexity of your system into your infrastructure. That's basically how you get Kubernetes, right? Makes it sound like a bit of an infectious disease. Putting your complexity into your infrastructure is putting your complexity into the least replicable, most difficult thing to debug, most environmentally changeable and varied part of your system. Sounds like a terrible idea when you summarize it like that. It's the reason that a myriad of technologies over the years have gained this kind of bad reputation is because they've attempted to externalize the complexity of their software design into configuration and orchestration and like all the other hard to debug and diagnose techniques. And all they ever did, all those things did, was amplify the complexity that was inherent in the system rather than contained it in any way. So, if so much of getting the design of our system right is about resisting the urge to over-design and about resisting premature decomposition and resisting little cute visual representations, boxes and line drawings of data flows, what you really have to accept is that there's a truism that all architecture is fundamentally evolutionary. It always changes. Because it must, because it's temporal and based on context. It doesn't matter whether you like that or not, it's the truth, just like you can't argue with time. The only real constant is that you don't know, and that your system is going to have to change as it responds to the changing needs of the people using it and the people building it. You have to understand that your context will change, so there's only ever a good design for now. And that's horrible when people want to build a system that lives like 30 years. But like 30 years ago was like 1995. Vanishingly few systems live that long. So this is really the foundation of evolutionary architecture, embracing that the best architectures are only the ones that are the easiest to change. And that is a capability you have to design into your system, which in itself was ironically one of the foundational threads of the microservice movement, that you can contain areas of your system and dispose of them as the requirements and context changes. And it's important to stress that a system having an evolutionary architecture does not mean don't do any design and just see what the fuck happens. But instead, that you're in a state of constant design and iteration, and you're doing more, not less design to enable growth and change. And if you embrace this as a reality that your architecture will change, there's this brief reprieve, right? There's a freedom from the expectations of getting everything right at the start because it's not going to happen anyway. And what is important, though, really, is that you at least try and understand that the things that could apply stress to your design and understand which things could possibly break it. So you're kind of planning for the unknown without building the thing. Taking a good educated guess at which aspects of the system might be exposed to additional load or feature creep or changing requirements is something that you should consider when you're navigating to that like initial first design. Now, it doesn't mean building open-ended extensibility points everywhere and designing capabilities that you don't necessarily need. That's over-design. But it does mean that you should make like whatever you expect to design and look at wherever you expect your design might shift. You should look at that piece. And you should be careful to not let assumptions from your earliest implementations creep into the core of the system. So one of the few useful things I ever heard Jeff Bezos say, I think he's got like 2 useful things, is that there are like 2 types of decisions. There's the ones that are easy to unmake, and the ones that are expensive to unmake. And in the early phases of system design, you should be focusing mostly on the decisions that are really easy to unmake, because you just don't know. And only when you start to navigate yourself through the problem space, start to make big bets on things that would be difficult to unmake. So the final superpower in building a design that's kind of fit for growth is to name your things, right? Your archetypes, the kinds of systems that you build and the techniques you use to build them. I love language. Love language. It's how humans form thoughts. It gives us a way to talk about ideas and critique them and kind of bring them to life. And it's vital that you design a system that you start to find meaningful names for the kinds of things that you build. Now, in my organization, I look after about 60 engineering teams, right, which is kind of vaguely terrifying. And one of the best things we did is we started to give names to the kinds of APIs that we were building. So we build domain APIs. That's where behavior lives, borrowing the name from DDD. We build composite APIs. They're higher order sets of behaviors that orchestrate over domain APIs. We build connector APIs that are anti-corruption layers and buffer against third parties. And by giving those kinds of APIs well-known names that everyone can communicate about, it actually changed the way we talk with our product people, because they can get that kind of abstraction into their heads. Like, language is truly power, you know. It's a lesson that was learned years ago by the domain modeling community and somehow lost in architecture, that just making up names for stuff is kind of useful. So in fact, as the systems I've been looking at have grown and found their shape, I found it interesting to come up with like slogans. I have a really exciting job, right? Just making up sentences. Brilliant. They're touch points, though. They help people guide what they're doing every day. So these slogans change based on context and what we're trying to achieve as a company at the time, but I've used them to keep people focused on the things I think really matter. So I use this phrase, capabilities, not customizations, which help guide us from a place of doing client-specific work and glorified hacks to building out like a more generalized set of features as we matured our software offering into a platform. And I could always say, hey, is this a capability or a customization? And I could push back on people's designs with that. Designing for substitutability, to capture our desire to allow our partners to bring their own components and work within our software ecosystem. Or even building a boring platform to help capture the idea that I wanted everyone to slavishly stick to only standards compliant and compatible things when they were doing what they thought was novel work. Now, as your systems grow, actually finding language to characterize them makes it easier for people making moment-to-moment decisions to do the right things. So I spent a lot of time talking about the subtlety in the process of design and how it's very uneven. But with something so often seen as subjective, people often try and find some science behind it. Now, by way of reference, Barry O'Reilly has been talking about and writing about what he calls residuality theory for the past 4 or 5 years. Now, I'm going to crudely sum it up and say, buy the book, read the book. This will muller the idea. But residuality theory is about summing up, is about simulating, this process of evolution at design time to try and find a design that is most resilient to stress and change. It's fascinating work, and I really recommend it. And what he kind of covers in the book is how, whilst you might know what your stress is now, you can actually randomize and simulate stress on a system and mathematically see where certain design characteristics recur. He talks about this kind of often, so I'd really recommend it if you ever get the chance. The stuff on YouTube. So as we wrap up, I want to tell you about something that I found personally inspirational when it comes to making like beautifully designed things. And it was going to a Tim Burton art exhibition. I don't think I could look more like a stereotypical goth saying, go and see Tim Burton, but fine. So there's this concept in design of regular form. And it comes from language, and it's the collection of idioms and defaults and standard ways of doing things. So people love using regular form because we're conditioned to see meaning in patterns, and especially when we're predisposed to those patterns. It's why design patterns in software stuck, right? It gives you something to anchor on that meets your expectations. Now, in software and systems design, I find it really fascinating that some of our most established patterns actually break from the regular form. So I always use the MVC pattern in web development as an example. Now, okay, has anyone not seen an MVC framework? Perfect, thank you. So in many common implementations, the semantics of object-oriented programming are bastardized by the MVC pattern. It uses classes to model interactions rather than data and associated operations. Like the classes in your MVC application are not really classes as you would traditionally look at them. But what they realized is, and this was a Rails thing, that they could make a glanceable design that was so understandable that no one stopped to say, wait a minute, that's not a class. Like, it kind of made sense that interactions with a web server were modeled as functions on collector. It was an obvious design trick. But it's not what classes are for. It's a complete break from regular form. And some of our most iconic and beautiful design comes from this really deep understanding of tradition and convention, and then changing elements of those designs to better serve the end goal. Basically pivoting to do something unique. So what does that have to do with Tim Burton? Well, Tim Burton, famous film director, you may have known him from Edward Scissorhands, the 80s Batman movies, Nightmare Before Christmas. He started off as a traditional animator, and he was working for Disney, I think. And he's known for a really striking and distinct visual style, where he's got these very elongated characters, and it's the through line across all of his work. And while it might seem obvious, when I went to see this Tim Burton exhibition, I didn't realize he'd started off as a traditional animator. And I went and I took a look at all of his sketchbooks, and they're boring. They're boring. All of the stuff that he did when he went through art school into his early 20s were really textbook, classic anatomical drawings of regular form. And I thought it was a fascinating parallel that Tim Burton spent probably a decade doing really, really, really regular form before he discovered that he could subvert regular form to better accentuate the aspects of his animation and his characters that he was trying to capture. He had to have this deep foundational knowledge before he could subvert it into something more beautiful, right? And I think that's something that I find personally kind of inspiring in software design, that we can do weird things as long as they make sense and are somehow better at achieving the goals that we're trying to get to. And I think, we can do our best works by doing this. So much of what I do now is just giving language to things to help people working in this kind of eternal cycle of design. And many of these lessons were really rooted in traditional service-oriented architecture with kind of lessons from domain-driven design thrown in. But what I'm really hoping is that the next decade of software sees this kind of renaissance of software and systems design that is done by everybody. Perhaps it's the thing that will both humanize and re-legitimize software architecture as a discipline, perhaps, by shaking off all the pretension and the history and making it something that everybody does every day. Because I think that if we can find a good language for this thing and become more mindful about the explosion of complexity driven into systems by the prevalence and availability of just pouring more technology onto the fire, we'll end up with something more ergonomic, beautiful, and fit for purpose, and we have a better chance of then building software that survives by making smaller things. It's okay to challenge perceived wisdom on the distribution of systems and componentization, and it's okay to break regular form, just as long as we build something that more intentfully captures and encodes its characteristics into the design that we're trying to make. Because your software has a design, even if you intend for it or not. Have a great rest of the conference. Thank you for listening.